Hello, calculus fans. Okay, let's try to determine a linear approximation. I'll give you this function, f of x equals cube root of x, and we're going to do the linear approximation at x equals 8. It's worth noting that this is a good place to do a linear approximation because it's easy to know what the value of f of 8 is. The cube root of 8 is 2. We always want to do our linear approximations at values where we know what the function is, where we can just plug it in and easily determine the value of the function. Once we have this linear approximation, we're going to use it to estimate the value of the cube root of 8.6. And finally, we'll be able to determine whether this estimate is an overestimate or an underestimate. So we're going to be coming up with an approximation for the cube root of 8.6. It's not the exact value. Whatever we come up with is a little bit too big or a little bit too small. And we'll be able to know based on what we know about the picture, the graph of this function. So let's go ahead and try to compute this linear approximation. So the first thing we need is to compute a derivative. So we rewrite the function as x to the 1/3, which of course gives us our derivative of 1/3 x to the minus 2/3, just using the power rule. Now we're using a equals 8. That's where we're basing our linear approximation on. So we just need to plug in 8 into the original function, and we get 8 to the 1/3 power, which is 2. The next thing we need to do is plug in 8 into this derivative. So for that, we get, of course, 1/3, 8 to the negative 2/3 power. So we're basically just plugging in 8 into this here. And now we've got to try to simplify this. So that negative power we can move down into the denominator. Now it looks like this, 1/3 times 1 over 8 to the 2/3. Now we can simplify this without using a calculator. We'll rewrite that as 8 to the 1/3 raised to the second power. We can do that because if you have a power on top of a power, then you just multiply those powers. And we're just using that property in reverse. That 8 to the 1/3 power just turns into 2, and so now we have the value of f prime of 8. So we just get 1/12. Now we're going to piece all this together to get the linear approximation. So if you want the linear approximation at x equals 8, it just looks like this, f of 8 plus f prime of 8 times x minus 8. Really, it's just an equation of the tangent line. And if we plug everything in, then we just get this. And just to remind you where these pieces come from, this 2 comes from here. That was the value of the function. The 1/12 came from here. That was the value of the derivative. And then the 8 just came from the fact that we're computing the linear approximation at x equals 8. Now that we have this linear approximation, we're going to use it to estimate the value of the cube root of 8.6. And in order to accomplish that, we're just going to plug 8.6 into the approximation. So the cube root of 8.6 is equal to f of 8.6 because f is just the cube root function. Now we're going to do the approximation. Whatever the value of f is, we don't know what that is, but we can say that it's approximately equal to L of 8.6. That's our linear approximation. And we have a formula for L, which is very nice. You see, the original function wasn't very nice. If I asked you what's the cube root of 8.6, you wouldn't be able to do that without reaching for a calculator. But now, if you have this function and I asked you to plug in 8.6 into that and do it by hand, you really wouldn't have that much trouble. In fact, that's exactly what we're going to do. So we're plugging 8.6 into this equation. And now we have something that's actually not that bad to try to simplify. So the 8.6 minus 8 turns into 0.6. And if we work all that out, we're going to get 2.05. Now this is an estimate. we're saying that the cube root of 8.6 is approximately equal to 2.05. Now we wouldn't know the more accurate value unless we used a calculator. Well, let's go ahead and do that now. I went ahead and plugged this into my calculator and got an approximation accurate to 5 decimal places. I got 2.04880. That's actually really close. You should see that this number is actually pretty close to this number. We're not all that far off. So depending on what we're going to use an application like an approximation like this for, this could be pretty good. I'd just like to take a look at a graph of these functions. So in blue is the original function, the cube root, and in red is the linear approximation that we came up with. So the red is a straight line, and it's just a tangent line to the curve at the point 8, 2. Now notice that the graph of the original function is concave down, or at least it is in here. That means that the tangent line approximation that we come up with is an overestimate. That's because the line, the tangent line, lies above the curve. Anytime you have a situation where the curve is concave down, that means the tangent line has to lie above the curve. So the tangent line approximation has to be an overestimate. We're picking, instead of a point on the blue curve, we're picking a point on the red curve, and that lies above the blue curve. So we know now it's an overestimate, and this is actually consistent with what we had calculated. Our approximate value of 2.05 was just a little bit bigger than the more accurate value that our calculator gave us, which was 2.04880. Now the very last thing I want to mention is that it was fairly easy to look at the curve and tell that it was concave down, but this is actually something that we can do analytically. We can compute a second derivative, and that information can tell us that the curve is concave down. So if you compute a second derivative, you'll get this, -2/9 x to the minus 5/3. Go back and look at what the first derivative looked like and convince yourself that the power rule will tell you that this is what the second derivative is. Well, this second derivative is negative when you're near x equals 8. That's because of the negative value out in front. And that's what makes the curve concave down. So even if you weren't able to get a picture of the original function, you could use this information, the second derivative, to tell you that the curve is concave down, which thus means any approximation based on the linear approximation will be an overestimate. Okay, that's all for now.